Okay, so the first thing to do for the pulley problems is to label on all the forces that are missing. So for these two particles, which are 5 kilograms, let's label on a force of 5g from each of them. Okay, so the question says we have a light inextensible cable, a frictionless pulley, and the system is in equilibrium. Okay, so there's no acceleration this way or this way. We're in equilibrium, so A equals 0. Okay, so we want to work out these tensions. Well, for the first one, what I'll do is I will draw a box around it to show what I'm looking at to start with. So for the first question, to work out T1, let's just have a look at this as a box. Okay, so for T1, we have essentially a tension and they have everything else within this box, in the green box, okay? So what's the mass of that box? Well, we're saying that the cable's light and the pulley's light. These two masses are 5 kilograms, so we'll say it's 10 kilograms. What's that weight down? Well, that's 10g. Therefore, T1 must be equal to that. So T1 must equal 10g. Okay? So that's for the first part, and that gives you your T1. So the tension that's keeping this whole system sort of where it is. Okay, so let's look at T2. In this case, I'm going to draw a different colour box around it to show what we're zooming in on. So let's zoom in on just this part here. Close that. Okay, so for this part, for T2, I'll put it out here, we have our mass, which is 5 kilograms, 5g down, T2 going up, it's an equilibrium, therefore T2 equals 5g. Okay, and in my final situation, you can probably work this one out. I've got this part, which I'm looking at, just this blue box. And so, looking down here, I have exactly the same situation. 5 kilograms, 5g going down, T3 going up, so therefore T3 must equal 5g. Okay, so in the end, T1 is 10g, T2 is 5g, and T3 is also 5g. Okay, and it's perfectly acceptable to leave them in terms of g. Okay, so the first thing I'm going to do for this question, well, the first thing I have done is I've drawn a red box around this particle. So I've zoomed in on this particle and I've drawn a blue box around this particle. We'll come back to that in a moment. The first thing you need to do is label the forces on. So the force here is 2g and the force here is 5g. It's also a good idea to get an idea of what's going to happen in this question. So when this is released from rest, I think it's pretty obvious. You can see that this particle is going to move down and this particle is going to move up. Okay, so we can put our accelerations on here. Okay, we'll come back to this red and blue situation in a moment. The first question is to find out what T1 equals, and this is very straightforward. I hope you can see that the total force down is going to be 2g plus 5g, which is 7g. So T1, the force acting to hold this whole system up, must be the same as the whole force acting down. We're assuming that the pulley and the cable are weightless. So we have 7g down, which in newtons is 68.6. Okay. Right, now to get into this next part, we want to know what happens, what the acceleration is and what this tension is. So we have this red box and we have this blue box. So what I'm going to do is I'm going to treat the red box as my first sort of equation, and I'll treat my blue box as my second equation. So the whole point of connected particles is you can always simplify a problem by zooming into one particle and then zooming back out to look at the whole picture. So for this one, for equation 1, we have a particle, 2 kilograms, tension going this way, weight going this way. Now we know that the tension must be greater than the weight because it's moving upwards. Okay, so we can write T minus 2G, that's our force we resolved, equals MA, which is 2A. Okay, so T minus 2G equals 2A. We've got an equation with an unknown of T and an unknown of A. So that's my first equation. My second equation is this blue situation. So I'll draw this as well. So this we'll call number 2. And in this case, very similar, but going the other way. Okay, so in this case, I have 5G going down, T going up, which means that I can write an equation. 5G must be bigger than T because it's moving downwards. So I write 5G minus T equals 5A. Okay, and that's my second equation. Now, this equation here has come from F equals MA. Okay, hopefully we can see that and we're getting used to using this. That's all started with the equation F equals MA. We've worked out the resultant force on the left-hand side. On the right-hand side, we have the mass times its acceleration. Okay, well, we need to solve this simultaneous equation. We have 2 unknowns in each. You can do this however you want. I'll just go through a quick method for how I've done it. It's not exhaustive, there's other ways of doing it. So let's have a look. So I'm going to work down here. And the first thing I'm going to do is I'm going to rearrange both equations so they're T equals. Okay, so my first equation will be T equals 2A plus 2G. And my second equation, if I add the T over and then subtract the 5A, I'm going to have T equals 5G minus 5A. Okay. Now this second equation makes a little bit more sense. If you think about it, the tension must be the difference in these two forces. So 5G minus 5A makes a little bit of sense, but you can think about that yourself. In this case, they're both T equals, so I can therefore write 2A plus 2G equals 5G minus 5A. This quickly drops down to 7A equals 3G. So my acceleration is going to be 3G divided by 7. Okay, so my acceleration comes out to 4.2 ms to the minus 2. Okay, so we found the acceleration. Now all we need to do to find the tension is take one of these equations and substitute this value back in. So you can choose whichever one you want. I'll choose the first one. So T equals 2A plus 2G. Okay, so 2 times A is 2 times 4.2 plus 2G. Okay, in numbers, this is going to be 8.4 plus 19.6. Okay, 2 times 9.8. Okay, so the tension comes out to a nice round number. It comes out to 28 newtons. Okay, this is a very standard type question. This here, where you've equated the T's, is probably the easiest way to do it. You could try and multiply these so you get your A's the same. That's fine. I think what you'll find is you're always going to get single T's, so you can always find those. Another way you could have done this is by elimination. Okay, we could have added these two together. If we'd done that, we would have got 7A equals 3G on this side. That's also fine. I always tend to kind of write them out like this. Okay, so to summarise, T1 right at the start is 68.6, T2 28 newtons, and the acceleration is 4.2. Okay. Okay, so just like with the last question, I'm going to start off by labelling on some forces that I need. So this one's going to be 2 mg, this one here is 3 mg, and I'm also going to split up and sort of zoom in on the two particles, ready to create my simultaneous equation again. There we go. Okay, so first question here, we want to know what T1 is. Hopefully this is bread and butter stuff now. T1 is going to be 5 mg because it's the total force downwards equal to the force holding the system up. Okay, from this point, let's split these two particles up. Let's go for the red box first. So the red box, we have 2 mg going downwards. Upwards we have the tension, and we have a mass of 2m in the box. Okay, now we know that m is the same in both, therefore 3m must have more mass than 2m. So this particle is going to go down and this one's going to go up. So again, in this case, T is greater than 2 mg. So we go T minus 2 mg equals 2ma. Okay, that's our first equation. Let's put our blue equation on now. So I have 3 mg going down, T going up, 3m. Okay, it's going to go downwards, so I can write 3 mg minus T equals 3ma. Okay, so for this one, what we could do is we could rearrange them for T to start with, or I could do a substitution method. So let's do a slightly different method to the last question. Let's combine the two equations. Remember, this one is number 2. So I'm going to add these two together. So if I add them together, so I do 1 plus 2, I will get rid of the t's by doing this. I'll end up with mg on the left-hand side. On the right-hand side, I will have 5ma. Okay, so to find the acceleration, the first thing you know is we can get rid of the m's, they cancel. I end up with g equals 5a, so therefore a must equal 1/5 of g. Okay, 1/5 of g as a decimal is 1.96. Although both answers are perfectly acceptable. Okay, so I've got my acceleration. Let's find my tension. My tension, let's rearrange the first equation. So we end up with T equals 2ma plus 2mg. We put in this acceleration to find out what the answer is. So T is 2m multiplied by 1/5 g. Notice how I'm using g this time because, well, this one's in terms of g, so I can make my life a little bit easier here. So this means my T is 2m brackets 1/5 g plus g, just factorising it there. That gives you T equals 2m multiplied by, well, this is going to be 6/5 g. So that's 6/5 g, times it all through by 2, we're going to get 12/5 mg. Okay, now it's probably easiest to leave it like this. That is a force because we don't know what m is. I suppose I could write it as something m. Let's see what that's going to be. That will be 23.52 m. You can see how that's not a particularly nice way of writing it. 23.52 m. Yeah, don't really like that. That's a bit gross. So let's quickly get rid of that. Go away. Get out. Okay. Let's underline this one. So that's a perfectly acceptable way of writing your answer. 12/5 mg. Again, we know what g is. We don't know what m is. We get this. Now, this question highlights quite a nice thing, which is that basically all these pulley questions are ratios between the two. Okay, so because we don't know what m is, it doesn't really matter. As long as you know the ratio between the two masses, we can work out what their acceleration is going to be. Okay, so just keep that in mind. But yeah, again, comes back to a simultaneous equation which you need to solve. Okay, so for this question, it's quite similar to the ones we've looked at so far, but it doesn't ask for the tension, it doesn't ask for the acceleration. It really asks for more of a Suvat style question. How long until it collides with the floor, and what's its maximum height? Okay, we are going to need to find the acceleration first, so let's do that to begin with before we tackle A and B. So if we label up this diagram, we have our tensions, we have our weights down, 4.2 G and 7 G. Okay, and let's write out these equations as we have done before. So for this one, we have 7G minus T equals 7A. I think we're happy that it's going to move down on the left-hand side, and B is going to move up because 7 kilograms is more mass than 4.2. So here's our first equation. Our second equation is going to be T minus 4.2G equals 4.2A. Okay, if we combine these two to get rid of T, remember we never actually need to find T, so you don't need to worry about it. So let's eliminate T. If I add these together, I get on this side 2.8G, and on this side I get 11.2A. Okay, so my acceleration comes out to 2.45. Okay, and that's the first thing to think about. So we've got the acceleration. We know that B is going to move up. With this acceleration, T is going to move down. So the first question is, how long before particle A hits the floor? Okay, so we have a Suvat situation to think about. So let's write out our Suvats. Question is how long? So we're looking for T. We know the acceleration. Let's put it here. Notice I made it positive. Let's think about positive as being downwards now. That will help us. V, we don't know what V is. I don't think it's going to matter. We know that U is 0 because it starts at rest. And we know what S is. S is 1.8 meters as given in the question. Okay, so it makes sense for us to use the Suvat S equals UT plus a half AT squared. Okay, we want to know how long, so we've got time, we've got U, we've got A, and we have S. Okay, so we can manipulate this equation. So UT, U is 0, so UT is 0. So we end up with S equals a half AT squared. Let's rearrange this for T. So times by 2, divide by A and square root. So I'll just leave it as T squared for the moment. So T squared is going to be 2S over A. So 2 times S is going to be 3.6 divided by 2.45. And then if I square root that to get T on its own, I end up with the answer of 1.2 seconds. Do a nice underline for that. Okay, so T is 1.2 seconds using that Suvat. Okay, so that one's done. Put a tick next to it. The next question relies on something we looked at in our first sort of episode of guard mechanics, where we had a particle going up, continuing to rise, and we found how high it gets before it starts to come back down. So a good idea here would be to think about particle B on its own. So what I'm going to do, I'm just going to redraw this diagram a little bit. So if we have our particle B, let's put it here. Okay, now if this is the ground, okay, it's gone up. Probably a bad place to draw this actually. I'll draw it from the ground here. So here's the ground here. Particle B has started here. Now, the most important thing is to see how far up it's gone so far. So far, it started 1.8 meters plus 20 centimeters above the ground. So it actually started 2 meters above the ground. So in here, right, I'm just going to start this whole section again. Okay, I'm going to start again now. Okay, so for question B, we need to think about what has happened to the particle B so far in this question. Well, it started a certain distance above the ground. Now we've been told that it starts 20 centimeters above A. It says it in the question here. So that means it starts 2 meters above the ground. That makes sense. And it's gone up another 1.8 meters. Okay, so its position when A hits the floor is 3.8 meters above the ground. Okay, so when A hits floor, B is 3.8 meters above the ground. And we're going to pick up what happens from this point on. Okay, so if this is our particle here, and it's starting here at 3.8 meters above the ground, let's see what its subsequent motion is. So we know that once this particle hits the ground, once A hits the ground, this acceleration has changed. Okay, the acceleration has changed. The acceleration now is just gravity. Okay, it's just going down with gravity. What we need to work out is what this particle's initial velocity was when A hits the ground. And to find that, we can actually use the velocity of A when it hits the ground. Okay, so let's do that to start with. So for A, okay, so let's start with the suvat. S is 1.8, U was 0, V is what we want to find, 2.45 is the acceleration. Let's ignore T, we don't need it. So if we use V squared equals U squared plus 2AS. Now U squared is going to go to 0. We end up with V squared equals 2 times 2.45 times by 1.8. If we square root that, that gives me an answer of 2.97 meters per second. So that's the speed that A was going when it hits the ground, and it's also the speed that B is going, okay, when that acceleration is removed. Okay, so we know that it's accelerating down at G, its current velocity is 2.97. Okay, and we want to know how much further up it goes until V is 0. Okay, so we want to find what S is. Okay, so we need to use this equation again. We need to use V squared again in order to do this. So we start with V squared equals U squared plus 2AS. We want to find this S, so let's rearrange it to start. Okay, so S is going to equal V squared minus U squared over 2A. Now in this case, my U is 2.97, my V is 0, my S I want to find, and my A is G. Okay, so I end up with 2.97 squared over 2g. Okay, now g is negative because it's going the other way. Okay, so we're going to say 2g like this. Okay, so if I square 2.97, divide it by 2g, these minuses cancel, I end up with s equals 0.45. So it goes 45 centimetres above the final position when A hits the ground. Okay, so what's the maximum height above the ground it reaches before coming to rest? Final thing to do is to add the 0.45 to this 3.8. Okay, so we end up with the answer 4.25 metres. Okay, so there's a lot to look at on that question. There's a lot that's going on. It starts with something quite familiar and then it goes into SUVATs. So just keep drawing diagrams, make sure you get your head around it, make sure you understand it so that you can understand each step that you're actually doing. Okay, so this question, we have 3 particles. We have 2 5-kilogram particles on this side and we have an 8-kilogram particle on this side. We want to find the tension between A and B, and we want to find the tension between B and C. So we're going to need to find the acceleration and the tension of this whole system. So let's find T1 first. And to do this, we can really simplify what's going on. So if I sort of redraw this up here really quickly, I can model this as quite a simple setup in that I have 2 particles, one of 8 kilograms and the other of 10. Now the reason I can do this, terrible drawing, but we'll get over that. The reason I can do this is because the cable between B and C is inextensible, so the force or the tension, whatever it is, sort of is combined in both. So it doesn't matter that I lump this together as 10 kilograms. If we turn this on its side, it's a little bit like what we had with our car and trailer situations. Hopefully you can see the kind of connection between that. So up here I have my pulley system and I have, this one's 8 and this one is 10. So we can work out the acceleration and the tension as we have all the way along. So I'll do this nice and quickly. Obviously 10 is going to move down, so our first equation is 10g minus t equals 10a. Our second equation is going to be t minus 8g equals 8a. If we combine these together, rearrange for t, we're going to end up with 8g plus 8a, and that's going to equal 10g minus 10a. If I follow that reasoning through, I end up with 18a equals 2g. So my acceleration is going to be 1/9 g, which is the same as 1.0, we'll round it, so 1.09 ms to the minus 2. Okay, so we've got our acceleration. If we put this acceleration back in, okay, let's put it into the first one, for example. Actually, let's put it in the second one. We have t equals 8a plus 8g. So it's 8 times by 1/9 g plus 8g. And that gives me a tension of 87.1 newtons. Okay, so we've sort of done what we're used to doing, which is finding the acceleration, finding the tension to start with. Okay, so that's T1. That's done. If we want to find the tension between B and C, let's think about our car and trailer problem. So these are both 5 kilogram. I've redrawn 5 kilograms. I've redrawn the diagram over here to help us. I want to find this tension here, T2. So what I'm going to do is I'm just going to think about the second particle, so the lower particle. So I'm going to sort of draw a circle around it like this. and I'm going to think about this particle and what it's doing. Okay, so the force down on it is 5g. The acceleration down is 1/9 g, or 1.09. So for just this particle, I've got 5g going down minus t2 going back up, and that equals 5 times by my 1.09, which is my acceleration. Okay, so my t2 is going to equal 5a, sorry, I take that back, that's wrong. It's going to equal 5g subtract my 5a. Okay, so my T2, my tension between B and C, is going to come out to 43.56 newtons. Okay, you can kind of eyeball that, it looks about right. 50-ish, take away about 5, that looks about right. Okay, so the tension is clearly different, and this method here is exactly the same as our car and trailer problem. So that's the tension between A and B, tension between B and C, that's done. The next part is a bit of a kind of, well, imagine what's going to happen next. So after 3 seconds, particle C hits the floor and ends up here. Obviously A's moved up. Describe the subsequent motion in as much detail as possible. It's kind of over to you here, but quite clearly the first thing that's going to happen, I mean, we don't know the distance between these two, but we can assume that B is going to travel down. Okay, so B is going to descend. I'll put some bullet points in. So B descends. It may hit C. Okay, so it may come down and hit C. But the whole point is, at this point, because C is touched the ground, we've kind of got a reverse situation. B is decelerating. Okay, A accelerates down. Accelerates towards the floor. Hopefully you can see this. Because we've reduced the mass on this side to 5, the A is now going to accelerate down, the B decelerates, or it goes back up. Once B's come to rest, A is going to start moving down. Okay, so once B comes to rest, A descends. Okay, that's not the end of the story though. What's going to happen next? A is going to descend until this is taut again. Okay, so A descends until, can't spell, there you go, until cable is taut between B and C. Okay, and at that point, C might kind of jump up a bit, but eventually it's going to come to equilibrium. Okay, eventually it's going to sort of settle down. Okay, the final bullet point you might want to include is equilibrium. Okay, and they'll end up at rest in this sort of orientation. Particle, cable, particle, something like this. Okay, they'll stay on the floor, A will be suspended, and that'll be the end of the story. And what a wonderful story it was. Okay, so you have 2 climbers at a climbing wall. You've read through this question. This is a legitimate problem, and it is bad practice when you're climbing. So we're going to find out at what velocity they're travelling when they collide. Usually what you do as a safety measure is have some sort of tethering system in the floor so that there's a kind of way of safeguarding yourself, or you'd have another pulley over here which kind of breaks up and gives you a sort of another force to help you. Anyway, whatever. I've redrawn this diagram like so as a simple pulley. So our heavier climber, so our 80 kilogram climber, is higher up, so he's starting on the wall, and the 50 kilogram climber is the one at the bottom on the floor. Okay, so it starts at rest because he's climbing, so there's no real tension in the rope here. When he falls, he falls from 6 meters. Okay, so what we'll do to start with is we'll work out at what acceleration this occurs. So the 80 kilogram particle is going to fall, the 50 kilogram particle is going to rise up. Let's work out A. We don't actually need to find out T in this question. Often it's worth just finding out anyway, but if we scan ahead, I don't think there's any reason to do it, so let's not worry about that. So let's start with our first equation, which is going to be the climber on the wall. So that's 80 G minus T equals 80A. And our second equation is going to be T minus 50G equals 50A. Okay, so as we've done before, if we rearrange for T and get rid of the T, or if we simply add these together, we end up with 30G on this side. Okay, the T's cancel. And on this side we have 130A. Okay, so our acceleration is going to equal 30G divided by 130, which gives us 2.26 meters per second. Okay, so that's our acceleration for both climbers, remember. So in all these situations, that what happens to one happens to the other because they're connected by an inextensible cable. Okay, we know that they're going to meet, well, if the climber falls 3 meters, then this climber here must rise up by 3 meters. And that should make sense, otherwise there'll be some sort of stretch in the cable, and that doesn't make sense at all because we've already said it doesn't. So they're going to meet when they both travel 3 meters, so it doesn't matter which one you choose. You know, they're going to be the same situation in both cases. They're both starting with a velocity of 0. So let's draw out our suvat. Okay, let's just check the question again. We want to find the speed, or we want to find the velocity, I should say. So we know that S is 3 meters. We know that U is 0. I'm going to go the climber at the bottom going up. So that's V, positive V, and A is 2.26. Okay, so we need to use our old friend V squared equals U squared plus 2AS. V squared is going to equal, well, U is 0, so V squared equals 2AS. So it's 2 times by 2.26 times by 3, and then we square root it, and that gives us an answer of 3.68 meters per second to the minus 1. Okay, now the question asks for the speed. The reason it asks for the speed is, if you think about it, one of them is going to be going 3.68 upwards, the other one's going to be going 3.68 downwards. Okay, so there'll be different velocities, but the speeds will be the same. Okay, so when they collide, both are travelling at 3.68. Now, this doesn't mean that when they collide, it's double that speed. It just means they both collide It's the same as sort of slamming into a wall at 3.68. Anyway, that's by the by. It's not a very good situation to be in, and it's dangerous. Okay, but you can see how there's a sort of real life application of these pulley questions. An exam style question. So very similar to what we've done so far, but a few more elements to it. Okay, so we're going to be looking at tension and acceleration, and then from that point on, we're looking at relating that to SUVATs. So let's start off with the first part. Three particles, 3m, 2m, and 2m. Two are attached together, so we can model them as 4m to start with. We want to find the acceleration. Okay. So I'm just going to draw a kind of simplified diagram for this really quickly. Okay, so over here we'll model this as 4m. On this side 3m, we have t, and we have 3mg down here, 4mg down here. Okay, so we want to find the tension and acceleration. So first things first, let's find the acceleration. Is to show that question, so we're told that it's a 7th g, so let's make sure that works. So we have 4mg minus t equals 4ma, and we have t minus 3mg equals 3ma. There are two simultaneous equations. We eliminate t by adding them or making them equal to t. And if we do this, we end up with mg equals 7ma. If I rearrange this, I can cancel my m's. I divide by 7, so I get a equals 1/7 g. Okay, so that's as required. Let's say show that question. Okay, find the tension in the string. Okay, well if I put that back into one of them, I'm going to choose the second one here. So we have t equals 3mg plus 3ma. A is 1/7 g, so I can write 3m 1/7 g. Okay, this gives me t equals 3mg plus 3m times 1/7 g. So we've got 3/7 mg. Okay, so we've got 3 plus 3/7 mg. So if I do 3 plus 3/7, I get 24/7. Okay, so I get 24/7 mg. Okay, obviously we don't know what m is, so this is probably the neatest way of giving this answer. Cool. So at the instant when A is 0.7 meters above its initial position, C separates from B and falls away. In subsequent motion, A does not reach the pulley. So it breaks this question down quite nicely, so it does it piece by piece. So when A is 0.7 meters above its initial position, we can find its speed. Okay, well, for this one we need to use v squared equals u squared plus 2as. We know that its initial velocity is 0. So it's quite a recurring theme here. We have v squared equals 2as. So v squared equals 2 times 1/7 g times by 0.7. If we square root that, we get 1.4. meters per second. Okay, so that's B. So for question C, it says find the acceleration of A at the instant C separates from B. Okay, well, essentially what we've got now is the same situation as we've got before, except instead of having 3m and 4m, we've got 3m and 2m. So I'm just going to draw this out again. It's always useful, just for your own kind of peace of mind, to redraw these diagrams just so you're completely clear on what's happening. So I'm going to redraw this diagram with what's left. So on this side I have my 3m still, and on this side I just have 2m because they've separated. Okay, so if I want to find the acceleration, we go back to this method that we've been doing all along. Okay, 3mg, 2mg. We know that it's going to want to accelerate this way now. Even if it's still moving up, it is accelerating this way. I hope that makes sense. So even if this 3m particle is rising, it can be accelerating in the opposite direction. And that effectively means it's going to be slowing down and then eventually will come back down and descend. Okay, so we have 3mg minus t equals 3ma, and we have t minus 2mg equals 2ma. Okay, if I combine these together, you know the method by now, I'm not going to bore you with it. We end up with A equals 1/5 g. Okay, so that's the acceleration. So I've done all this, done that, done that. Find the greatest height reached by A above its initial position. Okay, well, I'm going to try and fit this all on one sheet, so sorry if it gets a bit cramped, but I'll put D down here. Remember, if it starts at the bottom here, it's gone up 0.7, okay? It's then going to continue to go up until its velocity is 0. Remember, between sort of the bottom and here, it was accelerating at 1/7 g, and then as it gets to 0.7, it's now accelerating the opposite direction, 1/5 g. Okay, so it goes through two stages. It goes from 0 up to a velocity which is 1.4, then it goes up to 0 again. Okay, so all we need to do is use our v squared equals u squared plus 2as to find out what this distance is here. Okay, so we use v squared u squared plus 2as, and we know that the final velocity is 0. We have u squared, so we have 1.4 squared, and 2as, so we have 2 times by, now it's working against it, so it's negative 1/5 g times by s, which is what we're trying to find. So it's a little bit messy at the moment, but if I rearrange it, I end up with s equals 1.4 squared, which is 1.96, divided by 2g, so 2g over 5, or 2/5 g. When you work through this yourself, it will look a little bit less chaotic. Something's going strange on my computer. Okay, and this gives me an S value of 0.5 meters. So what we're saying is between this point here where it's going at 1.4 and to this top where it becomes stationary, it travels a further 0.5 meter. Therefore, the greatest height above its initial position must be 0.7 plus 0.5. Okay, so my final answer is 1.2 meters. Okay, so the last two questions I'm going to tackle together. These don't require any working. It's just more of a kind of a thought experiment, a way of thinking about what's going on here. So we've got Jeremy here who's, you know, set up a home gym. That's good for him. So it's not much to this. Essentially, we want to know what the maximum weight he can lift is. Well, hopefully it should be quite straightforward. The maximum weight he's going to be able to lift is his own mass. So if you think about it, if we have our pulley system and say he weighs, I don't know, 70 kilograms, this side is 70 kilograms as well, then he's not going to be able to move it because he's not going to be able to provide a force down which is going to be more than the weight up, if you see what I mean. You can't push down with more than your own weight. If this, for example, if this mass here was heavier than him, say it was 90 kilograms, and we had held this at rest and let go, he would go this way. We'd have to. I mean, there's just no two ways about it. You cannot, because your feet aren't attached to the floor, you can't provide more force than the force on the other side of the pulley. Okay. Now that's an important one. This type of pulley, remember, is just a simple pulley. So the force down here is transferred along here. Okay. And if he pulls down, the force goes up here. So he cannot, maximum mass he can put on is the same as his own mass. Okay, hopefully that makes sense to you. The next one, Lewis Carroll's monkey puzzle. I've given this problem to a lot of classes and it often stirs up a lot of debate. The key thing here is that it is frictionless. And this is quite a sort of wild concept when you think about it, because if it's completely frictionless, then this situation is going to be unlikely to happen anyway. If there's no friction at all, then even if these are exactly the same mass, say one of them is a gram heavier or a gram more or 0.1 of a gram more, it will move down because it's frictionless. Now, sort of keeping that aside, assuming that it does stay like this, which is highly unlikely, if the monkey starts to climb the rope, what happens to the mass? Well, you might think, okay, well, the mass stays in the same place, the monkey climbs up. But then if that's true, then this kind of bit of cable is going to be shorter, therefore this side's going to be longer. That doesn't make sense. It won't stay in the same place. And if it climbs up, what's stopping, how is it staying? How's the cable staying in the same place, which means it can climb? So that's not true. It doesn't move up. You might think, well, if it moves up, perhaps the monkey stays in the same place and the mass moves up. Again, nice idea, but wrong. What's keeping the monkey in the same place? If you think about this really deeply, what you should find is that actually if the monkey climbs the rope, the mass is going to move up at exactly the same rate. So what will happen is, as the mass moves up, the monkey will move up at the same rate. If it climbs the rope, it's got to equalise itself the whole way, and it's frictionless. So they're both going to travel up the rope at the same rate to keep it in equilibrium. Okay, otherwise there's a non-equilibrium situation which can't happen. Okay, so the answer is they both move up at the same rate. Okay, maybe not what you expected, but it's a good one to think about.